So we got assignment 4, 2017. And there's a little note here that's talking about these first two questions here. Is a very, very popular type of question. And even though some of the questions in your textbook might not list all of these things like this, they might only ask for a couple of them at a time. So it's almost like both of these questions were asked in chapter 2 and 3, but now it's almost like it's the exact same question as far as the process is concerned, but what you're asked to calculate is all thrown together in one. So just make a giant note of that. And the first question says, calculate all of these things you've learned so far for this reaction at 298 1 bar. So this is one of those classic questions where normally you start thinking it's going to be for delta H, delta G, delta S of the system, or the reaction, the products minus reactants. So you look at the end of your chapter, and so if I was framing this question, right, I would say, question 1. So you're going to have to balance this. You know, oxygen, and it's going to make iodine plus H2O, and that's liquid. Solid, this is gas, and that is gas. So if you're balancing this, there's 2 iodines here, which means this probably has a 2. 2 H's, there's 2 there. 1 oxygen, so this could be a half. So that's one way of balancing it. So normally what you do, you look up delta H naught F's from the back of the book. You look up the delta G naught F's, back of the book. And then you look up your entropies of the compounds themselves. And you can see how you make like a little sort of grid here. And that would go like that. So the back of the book, you look up each of these values, fill them in the table. Delta HFs and delta GFs by default, if it's your elemental form of these, oxygen, that's a 0, that's a 0, this is a 0, that's a 0. And then you look these ones up. So then you start, for instance, delta H of reaction. The naught means, of course, at 298. So your products would be 1, whatever delta HF of iodine was, plus 1 of those waters, delta HF of H2O, subtract off the starting material, so 2, whatever the delta HF naught of HI was in the back of the book, plus 1/2 the delta HF naught of oxygen gas. And you get some number, and the units are in kilojoules per mole. And then you do the same thing for delta G, and then you do the same thing for the delta S of your reaction. They're all in the back of the book. It's products, subtract the reactants, you get a number. So that would handle, we've got delta H, delta G, delta S. Now, one of the things about this type of question is when we move on to, so we've got that, we've got that one, we've got that. Work and heat, for instance. Well, this question has stated it's at 1 bar, but a lot of your textbooks, they'll go ahead and they'll just say it's at 298. And they leave this as, even if they don't say it in a question, it's kind of assumed that the pressure will be constant through the process. So whenever that's the case, if the pressure is constant, ... by definition, delta H equals the heat of the process. So whatever number you get for delta H here, because the pressure was constant, the value of Q will equal delta H. So now we have Q, and we're going back to thinking about how even when you did chapter 2 and test 2, you were definitely up to all 4 of these things right here. So how would we go after work or delta U? Well, we know that by definition delta H is equal to delta U plus delta PV. So one of the things we did was talk about how, unless we're told otherwise, it's always an ideal gas. You know that PV equals nRT. In these types of reactions, we normally say to ourselves, if the left-hand side of this equation is changing, what is changing on the right-hand side? And because this is an ideal gas law, this number of moles refers to the number of moles of gas. We make the assumption that things that are in liquid or solid form have very little effect on any volume changes or pressure because they're so negligibly small. But gases occupy a lot more volume and hence exert pressure. So we'll just track. So the change in number of moles of gas, the temperature is already deemed constant. So the change in the PV quantity is coming for what is the change in the number of moles of gas. The way we've balanced it to get this answer, you've got 1 mole of gas, so number of moles final minus number of moles initial. And the number of moles final is 1, because that's your iodine. And then initially you've got 2.5 moles, so subtract 2.5 equals negative 1.5 moles. So the change in number of moles is that. So we could say, I'm going to solve for delta U. So delta U will equal delta H subtract delta NGRT. Because we replace this with that. Solve for delta U. You should have the number for delta H here already. You know that delta NG is negative 1.5. You know what R is, you know what T is. So now you have that. So moving on, we also know from your second test or chapter 2, the first law of thermodynamics gives us one popular equation to use relating these things. We have the heat and we have delta U, so the work will equal the delta U that we've just calculated, subtract off the heat, which is also equal to delta H. So now you've calculated work. Next up, we know that delta S of the universe equals delta S of the system plus delta S of the surroundings. We have this one already. We calculated it up here from product subtract reactants in the back of the book appendix, because that was the system, which is the reaction, right? The surroundings by default is the heat from the surroundings point of view divided by the temperature of the surroundings. It turns out, in other words, this is known as whatever the actual heat of the process was, but we put a negative in front of it. Because if whatever you solve for the heat Q that actually took place, it's the negative of what the system's point of view. So whatever number that was for the system, the negative value of it, the actual, not some reversible special one. And the temperature of the surroundings, we understand, is assumed to be the same as the constant temperature of the reaction, 298. So you easily can calculate that. And therefore, add these two gives you that. So we're good with that. So now what we're left with is, let's see if I can fit this sort of on one page here. We know that by definition, Gibbs free energy is that. Entropy of the system or the reaction, the temperature. And if you put this in differential mode, Now, what do we know happened in this question? We were told that the temperature was held constant. So any change that takes place in Gibbs free energy is related to these three terms, but this one is out because there is no change in temperature in this question, so that's out. This, when you integrate it, state function, and ds, s is a state function, so this becomes change in G is equal to the change in H minus the temperature. When it's held constant, you can just put one value of T there, delta S of reaction. We have this, we have delta S, and we have the temperature, so you can calculate that. So that is okay. And then it turns out that Helmholtz is very similar, but it's U minus TS. So when you look at a change in that, right, temperature is constant, that's out. Integrate this, it's delta A equals delta U, which we know, minus T delta S of the system. You have these, you can calculate A. So where are we at? We're all done. So that is the basic outline and process of how to answer question 1.